Alright, so in this video, we're going to take a look at the difference between a reversible and an irreversible process to add one more bit of complexity to the mix of equations and tricks that we've cooked up. To recall from last time, remember that we had derived the Gibbs fundamental equation that delta G is equal to delta H minus T delta S. However, we had also shown that delta H is equal to Q, the heat of the reaction at a constant pressure, and we had previously shown that a change in entropy is equal to Q divided by temperature. Rearranging our equations, we could show that delta G is equal to Q minus Q, and then must always be 0. This statement is true for a reversible process, but it is not true for an irreversible process, and we'll be going over that today. Let's figure out where that difficulty could be. First, let's return to our definition of the Gibbs free energy from last video. That Gibbs free energy is equal to the internal energy of the system plus the pressure times the volume minus the temperature times the entropy. This definition isn't derived from anything else. We simply declare that the quantity that represents internal energy plus the pressure times the volume minus the temperature times the entropy is the Gibbs free energy. So we seem to be all right here. Next, we define enthalpy as being the internal energy plus the pressure times the volume similarly. So substituting this in here, we see that the Gibbs free energy is equal to the enthalpy minus the temperature times the entropy. We can take the derivative here, and assuming that temperature is constant, we get that dG is equal to dH minus TdS. So once again, everything seems to be all right here, and there must be something wrong with our substitutions. Let's first turn to the issue of enthalpy and defining it to be the heat of the reaction. A quick recap of how we did it last time. As we just mentioned, enthalpy is internal energy plus pressure times volume. If we differentiate, we get that dH is equal to dE plus VdP plus PdV. We stated that the pressure is constant, so dP is equal to 0, and we get that dH is equal to dE plus PdV. In our first derivation, we substituted in the first of the fundamental thermodynamic relations, which involves energy, and that is that dE is equal to TdS minus PdV plus the chemical potential term. If we also require that there's no change in matter during the reaction, we drop the chemical potential term and we are left with dE is being equal to TdS minus PdV. Substituting this in, we see that dH is equal to TdS, but as we had determined that delta S is equal to Q divided by temperature previously, the change in enthalpy must be equal to Q. However, we can also determine this without this substitution. Returning to dH being equal to dE plus PdV, we turn these infinitesimally small changes into deltas, and we see that delta H is equal to delta E plus P delta V. We know that the first law of thermodynamics states that delta E is equal to Q, the heat of the reaction, plus W, the work of the reaction, so we go ahead and substitute this in here. Assuming only mechanical work is performed, and the pressure is constant, the work is equal to minus P delta V, as we showed in our last video, and we indeed see that delta H is equal to Q, and this appears to check out. Thus, we only have one final substitution to check out, and that is that the heat of the reaction is equal to the temperature multiplied by delta S, and this is where our problem lies. This expression is only true if we have a reversible process. A reversible process is one that can go backwards and forwards, whereas an irreversible process can only go one way. Let's go through a couple of examples of this. Recall from our first video on entropy that we discussed that systems evolve towards a typical microstate that appears to maximize disorder. The example that we used was a box of particles that was partitioned, where only one side of the box contained particles. If we remove this partition, the particles would fill the entirety of the box. This would be considered an irreversible process, where our particles would never return to one side of the box due to the number of ways that they could spread out over the entire box. The change in entropy from the first state to the second state was positive. For any process, the total change in entropy of the system and its surroundings must be greater than or equal to 0. However, we also examined reversible processes. Take, for example, in our second video on entropy. We considered a system that we partitioned into two parts, and we allowed an infinitesimally small amount of energy to move between them. This change is considered reversible, as is any infinitesimally small changes. This is how we determined our definition of temperature, and was under these circumstances that we derived the relation of the change in entropy to the heat of the reaction divided by the temperature. This equation was only valid because it was a reversible process. We are now moving into true chemistry, and that is the study of reactions that are at equilibrium. For the reaction at equilibrium, the molecules themselves are not static. Take, for example, some vinegar dissolved in water. At any point, a certain number of vinegar molecules, acetic acid, will have lost their acidic hydrogens to form acetate. However, the equilibrium is dynamic, and some acetates will be gaining back their hydrogens as some acetic acid molecules are losing them. However, the concentration remains constant, and thus it is a dynamic equilibrium. Let us consider an even simpler process, the boiling of water. At exactly 100 degrees Celsius, water is at an equilibrium between the liquid state and the gaseous state, and they coexist. Let's consider the heat of moving a water molecule from the liquid state to the gaseous state at this temperature. We know that we have to put heat into the system, so Q is positive. We must break the bonds between the liquid water molecules, but once the water molecules are in the gas phase, they are free to move around, and thus the entropy increases. At this temperature, moving a water molecule from the liquid phase to the gas phase is a reversible process because it can easily go back to being with the liquid as both phases exist at equilibrium. Thus, delta S is equal to Q divided by the temperature. There is a certain heat and a certain entropy that is associated with this process. However, let's suppose that we raise the temperature just a bit. At this elevated temperature, the heat required to break the bonds is the same, and the entropy gain of moving the water to the gas phase from the liquid phase is the same. However, because the temperature has increased, delta S cannot be equal to Q divided by the temperature. Instead, because the denominator is larger, delta S must be greater than Q divided by temperature. At this higher temperature, the process is irreversible. At the higher temperature, all of the water is converted into steam eventually, and it will never condense back into liquid water. For an irreversible process, the change in entropy is greater than the heat of the process divided by the temperature. Thus, to encompass all possible processes, we now rewrite our equation as delta S is greater than or equal to the heat of the reaction divided by the temperature. Returning to our Gibbs fundamental equation, we make the same substitutions where enthalpy is equal to Q, but now T delta S is greater than or equal to Q, and as this has a negative sign, we see that delta G for any process that occurs must be less than or equal to 0. Now we see the true power of this equation. If delta G is less than 0, the reaction will proceed spontaneously and irreversibly. If delta G is equal to 0, the reaction must be at equilibrium, and the reaction is reversible. Next, let us consider one final concept. Suppose delta S for the reaction is negative. From what we talked about in the first video regarding entropy, you might think that this means the reaction cannot happen, as the number of ways that the system can be arranged has decreased. However, this is only true in a closed system that cannot exchange energy, such as heat. When we break our study into both the system and the surroundings that it can exchange energy with, we not only consider the change in entropy of the system, but also the change in entropy of the surroundings. Some would call this change in entropy the change in entropy of the universe, and in this case, we once again have a closed system, and yes, for any reaction, the entropy must increase. However, if the entropy of our system decreases, but the entropy of the surroundings increases the same amount or more, then the reaction will be spontaneous. Suppose that delta S of the system is less than 0, but delta H of the system minus T delta S of the system is less than 0. This means that delta H of the system is less than T delta S of the system, and as temperature is always positive, delta H of the system must be negative. We multiply this equation by -1, and we get that the negative change in the enthalpy of the system is greater than the negative temperature multiplied by the change in entropy of the system, and this equation will be useful in a minute. The change in enthalpy of the system is equal to the heat of the reaction, and any heat given off by the system must be absorbed by the surroundings. Thus, the heat given off by the system is equal to the negative heat gained by the surroundings, and we can multiply this equation by -1 as well. We substitute in the change in enthalpy of the system, and we see that the negative change in enthalpy of the system is equal to the heat absorbed by the surroundings. Using our above equation, we can conclude that the heat absorbed by the surroundings is greater than the negative temperature multiplied by the change in entropy of the system. At this point, we bring our equation for a change in entropy of the system, and we rearrange it to state that the temperature multiplied by the change in entropy is greater than or equal to the heat. We specify this equation to relate to the surroundings, and we substitute in our previously found equation. Moving everything to one side, we see that the temperature multiplied by the change in entropy of the surroundings plus the temperature multiplied by the change in entropy of the system is greater than 0. Temperature must always be a positive value, an interesting fact that we can explore in a subsequent video. So we divide by temperature, and we see that the change in entropy of the surroundings plus the change in entropy of the system must be greater than 0. As we stated before, this sum of entropy change is equal to the change in entropy of the universe, and thus the change in entropy of the universe is greater than 0, and the reaction is spontaneous, even though the change in entropy of the system is less than 0. This is why for any given reaction, it is better to look at the change in Gibbs free energy of the system to determine if the reaction is spontaneous, than to just look at the change in entropy of the system, because a reaction can still have a negative change in the entropy of the system and be spontaneous. This is why there is so much focus on the Gibbs free energy in chemistry. Thank you for watching this video on reversible and irreversible processes, as well as why the Gibbs fundamental equation helps predict the spontaneity of reactions. If you enjoyed this video, please like and share it, as it helps considerably in increasing outreach. If you want to see more videos on chemistry and physics topics, please consider subscribing to the channel. I linked my Patreon page in the description below, and if you would like to support educational content like this, please consider donating. Finally, please comment down below if there's something you feel like I could make more clear, or if there are other topics that you would like me to cover. Thank you.